All right, ground lesson 3B, instrument navigation, talking about the GPS. So what does GPS stand for? Well, it stands for Global Positioning System. So the Global Positioning System is a system that's comprised of 24 GPS satellites. It can change, one can drop out, but it's designed off 24 GPS satellites that have timed orbits, so at any given time you have at least 4 satellites, hopefully 5, in view at any given time. So these GPS satellites have varied orbits, so their orbits are actually pretty fast. So one satellite you may be using is going to be gone in a couple minutes. That's not super accurate, but you kind of get what I mean. So GPS relies on ranging and a word called trilateration. You probably heard of this. You probably heard of triangulation, determining your point, by triangulating it. And this is a similar principle, but in GPS world, it's called trilateration. So trilateration is essentially where 3 circles intersect is at a point. And so if we have the intersection of 3 circles, you can find where you are. So how does this work, apply to the GPS? So for the GPS in the Earth, we'll say this is the Earth down here. There's USA, okay? If you have 3 GPS satellites, and then they give out 3 circles, you can see how that lands you with a point where it intersects. Okay, so the 3 circles intersect at one singular point, and that point, you trilaterated your point, you triangulated your point, and that's how we know you're exactly here. So how do the GPS satellites figure out, what's the circle with a certain distance? How does that figure it out? So this is how it figures out. Let's just restart here. So let's just start with one satellite. And you're just kind of here. We'll just already assume you're right here. So the satellites operate on a principle which is very simple to understand. It's velocity equals distance over time. For example, miles an hour is a velocity. What is distance? Well, it's miles. And what is time? It's, a time per hour. So 60 miles per hour. There you go, miles per hour. Or kilometers per hour. So how it does this is the GPS is going to send out its radio wave at the speed of light. Okay, so that velocity is known. It's the speed of light. Okay, now we got to find a distance and a time. So which one are we going to figure out? Well, we want to know the distance, right? Because the GPS is going to figure out a distance from where it is. So it's trying to find the distance between you and the satellite. So how does it do that? Well, we can measure the time it takes. We can measure the time it takes from leaving the GPS satellite to arriving where you are. So we can measure that. So the GPS satellite itself has a very nice clock. It has an atomic clock. And so it's going to relay that down through the frequency to your receiver. So your receiver can figure out the timing it takes from the satellite to arriving at your receiver. So then you can figure out the time, and let's just arbitrarily say that took 1 second. So it took 1 second from it going from the satellite to arriving at where you are. Now you can figure out the distance, because you have 2 variables. Now you can solve for the other. So this is how it finds the distance. Now the distance, it's not going to know magically it's right here along it. It very well could be here, or here, or here, or here, or anywhere along a circle of possibilities. Technically a sphere. We'll just keep it easy. So a circle of possibilities. Why? Because let's just say this distance is 100 miles. Okay, 100 miles could be 100 miles here, could be 100 miles here, or here. So that's why GPS relies on trilateration, not just one satellite. Okay, so we have one satellite, and that's going to land you on a circle of possibilities. So let's bring in another satellite. So let's say another satellite does the same thing. It sends its radio wave down at the speed of light, and you time the time it takes from going from the satellite to arriving at where you are, and you figure that out, and that gives you a certain distance. I'm going off the screen here. So that gives you a certain distance. So now we just have an intersection between two circles. And I might draw that down here. So if you have two circles that intersect, you can now be in a range of possibilities. If we're circles, we're limited to 2 points. So now we just limited our possibilities to these 2 points. But here's the nice thing. If we use the Earth as one of these spheres, notice we can eliminate this top one because obviously the Earth isn't above the GPS satellites, right? It's down here. So if we use the Earth as that third sphere, we just trilaterate our position essentially, okay? So the Earth as one can figure out your latitude and longitude. So if you're at an altitude at all, let's say you're at 30,000 feet up here, this is not going to calculate your exact height where you are because again, we're assuming the Earth, you're on the ground. So by figuring out two GPS satellites, you can figure out your latitude and longitude. So latitude and longitude only, not your height. And so this is where this third satellite comes in. So if you grab a third one now, it's getting a little messy here, but that third one can now get you a longitude, latitude, and also an altitude. 1, 2, 3, trilateration. Now, you might know that it takes actually 4 satellites to determine your position. So why does it only take 3 to determine longitude, latitude, and altitude? What's the contradiction? Well, you need 4 because our receiver is not good. So the receiver in your phone, or your iPad, or your watch, or the car, or the airplane, they all have a quartz clock. So it's not an atomic clock. It's not a big, perfect clock. Now, an atomic clock isn't perfect, but it's pretty close to it, whereas the GPS satellites do. And because we're operating on velocity equals distance over time, it's super important we have this time exactly to the best of our abilities, because we're talking about huge numbers. So if the timing's off by just a little, that puts you in a whole different place than where you actually are. So how do we resolve this issue? How do we get away with a $5 Chinese clock? Well, how we get away with it is if we introduce a 4th satellite. And this 4th satellite will check for time. So this 4th satellite is basically, you're using that atomic clock and you're stealing this GPS satellite's atomic clock and then checking for your own time. Okay, so this is why you need 4 satellites, at least 4, for GPS in your airplane. So you need coverage of 4 satellites. Get this out of here. Hopefully that makes sense. So 4 satellites are needed. And if we want to be more specific here, how does the GPS, send its wave down, and how does the receiver pick it up and determine that timing part of it? How does it determine that timing? Well, the GPS is sending down at the speed of light something called the L1 carrier. So the L1 carrier is the frequency that's being sent down. And that's being sent down at, I think, 1547.56 megahertz. Okay, that's kind of an irrelevant number to know, but that's what's being sent down is this L1 carrier. Now, inside of this L1 carrier is 2 frequencies that have been modulated or added together. So if I add a frequency together like this, you get a frequency. So if you add these together, you get the carrier frequency. That's what modulating frequencies are. It's adding 2 together and then you get 1 output. So you have a modulated frequency, which is the L1 carrier, and that's what's being sent out to all the Earth. Within that L1 carrier, you have something called the course acquisition code. The course acquisition code. So each satellite, all 24, each have their own unique carrier, which is composed of their own unique course acquisition code and their own also a nav data. So the course acquisition code is really how you're measuring this time. So your receiver also has these course acquisition codes for each of the 24 GPS satellites. So essentially, you've got to think of these course acquisition codes like the blueprint of the GPS. So your receivers already has the blueprints to them, so your receivers already knows the course acquisition code. So now all your receiver has to do is just listen and see what it's receiving. So for example, let's just say satellite number 12 is in view right now, okay? So satellite number 12 is in view, and satellite number 12's course acquisition code looks like this, okay? So it looks like this. And then we're just listening, our receiver's listening to the GPS as it comes over, and then we hear this. So we hear this. Notice this is the same exact pattern here. Do you see how this is the same pattern? Maybe you didn't do a good job drawing it, but notice it's the same pattern, but there's a little bit of a lag between the start of it, when it's supposed to start, and then when we actually hear it. So this difference right here between it is that time. So we can measure, each one of these are individual bits. This might be 1, 0, 1, 0, 1, etc. So we can measure how many bit difference there is between when it should be and when we receive it. And so that's how they measure time. So the GPS spits out 1,023 bits per millisecond, which means it sends out 1,023,000 bits per second. So each one of these are bits, 1, 0, 1, 0, and so it's spitting this out 1 million, sequence long every second, okay? And so this is where it's actually pretty smart. So you have 1 million bits per second. And then we know that the speed of light is 30,000 kilometers per hour, or 300 million meters per second. So if you do that math, we can then get a resolution of 300 meters. So do that math, that gives you a resolution of about 300 meter accuracy. So just based on the way it's built, we can get up to 300 meter accuracy. Now the nice thing is you can actually measure, which I didn't erase this, but you can actually measure not only just like hard lines, but also where they transition as well. And so just by reading the GPS alone, you can get to about 30 meters of accuracy, which is very good. So there you go. So you've got a CA code and the nav data as well. So if you've ever started the GPS on an airplane, like a commercial airplane, let's say you pulled out ForeFlight on your phone on a commercial flight, and you've noticed, you don't have Wi-Fi or cellular, and you've noticed it takes several minutes for it to boot up and give you GPS position. Whereas if you just open ForeFlight, let's just say at home, or if you have cellular data, the GPS position kicks up really fast. Now the reason for this is because you have something called a cold start. So the GPS is also going to send out nav data associated with this. So it's going to send out things like ephemeris data, corrections for the ionosphere or something like that, and also it's going to send out info regarding about the satellites. So it takes a while for you to receive all this information, and usually it takes about 12 minutes or so from a cold start to being able to actually actively use the GPS. So this is why it takes a lot longer to boot up when you just flick it on, because you're in a cold start process. Now it's nice, the reason why it goes so fast when you're on cellular or Wi-Fi is because your phone can download that ephemeris and nav data just over the cellular network, plug it in, and you're good to go. Okay. One question before we move on is, how does the GPS system accommodate, close to 6 billion users all at once? Like for example, if I had AirPods in, I can only connect them to my phone. So the reason why you can have so many users on the GPS is because it's a passive system. So anybody can listen to the signal. For example, if I saw a meme where if you could fit like everybody in the whole world into Central Park, into like a giant meatball. And so if you had a very loud megaphone, everybody in the world would be able to hear you. So why would everybody be able to hear you? Well, because everybody's just listening. There's no connection. You're just listening to the waves. Similar to how everyone on the earth is just listening to the signal. So it's a passive system. So GPS is a passive system. One more thing before we move on. GPS, that's just how basic GPS works. How does your GPS measure ground speed as well? If you ever wondered, how does Waze know I'm speeding right now? How does Apple Maps know I'm speeding? How does it figure that out? Well, what's interesting is you only technically need one satellite to figure out your ground speed. So this satellite sends out its wave, its carrier signal to you, and you receive it. Now, if you start going faster than 0 miles an hour, let's say, so if you go faster than that, what happens is that wave, as you listen to it, experiences a Doppler shift. So, for example, when the fire truck is screaming down and you hear the sirens go, ooh, what you're hearing is that Doppler shift. So your receiver is able to pick up on the Doppler shift that it's hearing from the wave. So the faster you're going, the bigger that Doppler shift is. So then it can correlate that into a ground speed. So then if I have maybe like, let's say 7, 8, 9 satellites in view at once, I'm all listening here, and so I just figured out 9 solutions to my ground speed. That's gonna be a very accurate reading because I can now compare 9 solutions and then get my ground speed from that. So your ground speed relies on a Doppler shift of the wave. That's pretty interesting. Let's talk about the GPS errors. So you can just write these down. I guess some rote knowledge. So the first one, you have ionospheric delay. So ionospheric delay is just the error in pseudorange as a result of passing through the atmosphere. So the Earth has something called the ionosphere. I need to research it a little more. But essentially, as it passes through, it can alter these GPS signals a little bit. So that's why it's sent through the nav data. That way it sends the appropriate correction data so your GPS can work good. You also have ephemeris errors. Ephemeris errors. And so this is orbital variation caused by gravitational effects on the Earth or the moon. So for example, if you have a different moon phase, you can have an ephemeris error. So at first when these guys in the 70s were making GPS, they noticed all these errors that they had as well, because the Earth is not perfect in the sense that just the wave shoots down directly to you, no errors. Another interesting one, which you can look up on your own time, is general relativity, and also something called special relativity. So general relativity and special relativity, I really don't feel like explaining this, and I don't think I could give you justice for this explanation, but essentially when you're moving faster, there can be some delay on how you're hearing it. And so the GPS actually does take this into account, and this is one of Einstein's theories. That's might have where you've heard it before. I think there's a good Flight Insight video on it, or you can just become a physicist, either one. You have the cold start error, which is what I talked about. So we have to download the nav data so we can understand what the errors are today and associate that into our receiver. You also have satellite geometry. So satellite geometry is also one. So the big one for this is not really your latitude and longitude. So you have to remember, let's say I'm looking at Earth from above. So I'm looking at it like a bird's eye view. So I'm looking down on America right now. The thing is since I'm top down, I have a great view of where your latitude and longitude is, but I have a terrible view of your altitude. For example, if I'm looking straight down, it's hard to tell if that object's all the way up here or all the way down to the ground, or 100 feet from the ground or 0 feet on the ground. So it has a hard time doing that. So this is why your altitude error is always going to be greater than your positional error. It's because in order to get a better view of your altitude, let's say you're here, it'd be best to go from above and below you so we can see the difference. But since the GPS only looks from above, it's hard to tell that altitude. So this is why you need WAAS, for example, to shoot an LPV approach, because you're mainly concerned about the altitude. We really want to know your altitude. Because an LPV guarantees vertical guidance alongside the lateral. So vertical is altitude, right? So if you have a lot of error with your GPS, you're also going to have a lot of altitude error as well. So we really need to get that down as best as we can. And then finally you have something, which really isn't a problem anymore, called selective availability. Selective availability. So I don't remember, was it 80s or 90s, but essentially the GPS was for military use only. I actually think I have something written down about this. Yeah, so I think around the 80s, there was a Korean air crash that happened. I think they went into like Russian airspace and then got shot down. And so this led to Reagan making GPS available to the civilians, us, right, common earthlings. And so this made GPS available to everybody, not just the DoD or not just to the military. Now at first, they gave everybody GPS, but they put some selective availability on that, meaning that the civilians or civilian people would get GPS, but the integrity would be a lot lower. So they would purposely dilute the resolution so that the accuracy of your GPS wasn't very good. So there's nothing you could really do about it. And so, fast forward later on, and this led to something being created called differential GPS. So differential GPS is what also led to something called WAAS. You might have heard of WAAS before. So let's talk about differential GPS. So again, because of the selective availability, what the Coast Guard did is they figured out a way to bypass the selective availability and make their GPS very good. And so it works on, and so that's called, again, differential GPS. So differential GPS works on the principle called augmentation. So augmenting something. So when you think of the word augment, it usually means to replace or change or to build something better. So like in cosmetics, I guess you would augment your face or your nose or something like that. So you're changing it to make it better. So GPS augmentation. So the definition is a system that aids GPS by providing accuracy, integrity, availability, and other improvement to positioning, navigation, and timing of the GPS. So how they did this is pretty smart, by the way. So how they did this is they have something called a ground station. Okay, a ground station. So the ground station in layman's terms is your house, okay? So let's say you live at your house and you know exactly where your house is. You know it's on this address at this street, and you know exactly the coordinates as well, latitude and longitude. So then if you know where your house is, you can then put a GPS receiver on your house and ask the GPS, hey, where am I? And where am I, And the GPS may say, hey, you're in the neighbor's house over here. And you're like, no, I'm not. I know where I am. The GPS receiver is on my house. Okay, so the GPS then has an error of this much. Let's just say the error is 100 feet to the right. So the error is 100 feet to the right. Now, if you have a plane flying near your house, the GPS is going to give that same error. So the airplane, it may be exactly here, but the GPS thinks it's here. It's 100 feet to the right. So what we can do then is tell the airplane, hey, I know I'm here, but it's reading 100 feet to the right. So just subtract 100 feet from what the GPS is telling you, and that's where you really are. So if we subtract that 100 feet, look at that. The GPS position is now exactly where our airplane is, and we've gotten rid of that error associated with the GPS. So this is how GPS augmentation works. Now specifically, the augmentation system that we use is called WAAS in the United States, WAAS. So Wide Area Augmentation System, WAAS, Wide Area Augmentation System. So it's going to work on this same principle. Now what it does is they have 38 of these ground receivers set up all across the United States. So chances are, you know, if I sprinkle these around the United States, they're spread out, so at any given time, you're pretty close to one of these ground stations. For example, in Ohio, there's one in Cleveland. I think it's where the ARTCC center is, so it's in Oberlin. So they have one of these in Oberlin, which means if you're flying nearby, chances are you have a pretty good correction, a pretty idea of that correction. So what it does is you have the ground station, and that ground station can figure out its error. So then you have a computer in the ground station saying, okay, it's this error, let's send that out to all the planes. So then that sends it to a master station. So the master station is just a fancy building, and then that master station will go and then uplink it through one of the dishes up to something different called a geostationary satellite. So this goes from your ground receiver to a master station, uplinked to a geostationary satellite. Now these are just, now there's 3 of them that WAAS system uses. I drew them here. One of them I think is the SPS 15. So these are just commercial, these are commercial satellites that have different features on them. So really the FAA just bought, you know, a bandwidth of it, and we're using that. So these geostationary satellites, geostationary meaning it sits in one place and the orbit is timed so that at any given time it's just sitting right above you. So as the Earth spins, the timing of the orbit is such that it looks like it stays over us the whole time. So the orbits will stay over us the whole time. Now your airplane's here, right? So then from the geostationary satellite, it's sent to your aircraft, to your GPS, and then can apply real-time augmentation data to it, therefore correcting your GPS. So you saw how we went from the receiver to the master, uplink to the geostationary satellite, to your GPS, and now you've augmented your GPS and we've created a more integral GPS. Okay, so again, the biggest advantage is that it solves for the vertical error. Remember, it's very easy to find our latitude and longitude, but it's very hard to get that altitude. For example, just check your 430 or check whatever 530 or whatever you're using, 355. Go to the system page with the GPS status and look at the estimated position error between the vertical and your horizontal. It'll usually be about double, depending on where you are. And the biggest advantage with the WAAS system is if we have a WAAS enabled GPS, meaning we can listen to this. If we have a WAAS enabled GPS, we can fly LPV approaches. So other words we should know in regards to augmentation is also something called LAAS, LAAS. So this is again similar thing to WAAS. So it's more of a localized WAAS though. So LAAS just stands for local area instead of wide area, local area. So what they can do with the local is then if you have an airport, these are runways. If we have an airport, we can put one of those ground stations on the airport. So then our correction data is very good. Because think about this, if I'm flying way out here in the ocean, my nearest receiver may be on land. So chances are the error associated with it might not be very good. So we may be able to solve for some error, but it may not apply for you. So really that correction you just did was for nothing. But if I put one of those receivers on the airport, my corrections can be very, very good because it's very close to me, right? Here's my plane landing, okay? And so using this WAAS system, we can make something called a GLS approach. Now this is not practical to us because we'll never be able to fly one of these until we get a big boy plane. But a GLS approach just stands for GBAS landing system. And that GBAS is kind of what we were talking about here. Ground-based augmentation system landing system. So ground-based augmentation landing system is your GLS approach. And so essentially all it does is it, instead of uplinking it to a geostationary satellite, let's just say we have this, like that. Instead of doing this whole action, we'll just send it via VHF to your airplane. So we'll just have a, there it goes. We'll just have a little cell phone tower and we'll uplink it via VHF to your aircraft. That's all it is. So only a handful of aircraft are certified for these GLS approach. It's probably the future of approaches. Although, how practical is it? Because you have to have all this set up with the ground-based, that local stuff. And there's only a few in the United States too. There's one in Newark, and then San Francisco, and probably some other place. I think Sydney is another one. They're only in several sites. Now, in regards to augmentation, we have one more thing about augmentation. And this one is important to know. And it's called RAIM. Now remember, a GPS unit can be either WAAS certified or non-WAAS. So if you're non-WAAS, you're hopefully going to have RAIM on board. And RAIM, what that stands for is Receiver Autonomous Integrity Monitoring. Receiver Autonomous Integrity Monitoring. And so unlike normal GPS, which requires 4 satellites in view, RAIM's gonna need one more. So it's just gonna need one more. So you're gonna need 5 satellites in view at any given time. And so essentially, RAIM is, on its own, and it's in the background. So it's monitoring the integrity, but it's autonomous, okay? So really what it's doing is it's just checking to ensure that each satellite is doing what it should be doing. So for example, this one's reading right, this one's reading right, this one's reading right, this one's reading right, this one's reading a bizarre reading. What we can do then is say, hey, this one's not reading right. Okay? So this is something called fault detection. Fault detection. Additionally, if we have a 6th satellite, we can do something called exclusion. And this is where this word fault detection exclusion comes from. Because if I have a 6th one, I can axe this one and say, hey, you're gone, buddy. But then keep my RAIM, because then I have 5 to do RAIM. So again, if I have 6, I can axe 1, keep 5, and I can keep my fault detection going. Now I'm going to lose the exclusion unless I pick up a 6th one. So that's RAIM in a nutshell. One more thing with augmentation and that sort of stuff is you also can have something called a barometric aiding GPS. So you can have a barometric aiding GPS. And this is obviously only going to require 4 satellites, but it also requires a barometric altimeter to detect the RNAV integrity. So it's just going to use information from the pitot-static system, and then so it's essentially like an altimeter working along your GPS, so it's aiding the GPS. And so this is where on the approach plate you see that LNAV, VNAV minimums. So in order to do these, you need a barometric aiding GPS. So that pretty much wraps up the augmentation side of it. So really the GPS you can fall into are either non-WAAS units, because in this day and age, WAAS is the king, or WAAS units. So non-WAAS or WAAS, initially you're going to have LAAS, LAAS, but we'll just stick to these because this is what we're operating on. So your non-WAAS consists of TSO C129A and then C196. So these are going to be your non-WAAS, your RAIM GPSs. So the 129A is the minimum performance standard, and so this is going to need an alternate approved method outside of just pure GPS. Okay. The 196 is also kind of a revised version of 129A, except for it's optimized for ADS-B. So chances are, if you're a non-WAAS GPS, you're going to be one of these two. So I just did the work for you and told you those. The WAAS GPSs are going to fall into TSO C145A. Okay, and these are GPS augmented by WAAS, and these are incremental improvements to 129A, but essentially you get that WAAS capability with it. You also have C146C, and this is the standalone unit that can be used with no alternate means of navigation outside of GPS. So legally, when we talk about, if we bring our eyes down here, equipment needed, your SPS GPS refers to these right here, so your non-WAAS. So for equipment needed, I need something other than GPS. So for example, that could be VOR or other usable equipment. So I need some other option. So I need an alternate available, and usually the next best would be a VOR or an ADF or something like that. A WAAS GPS does not need any other equipment, especially if you're C146C. So you need to check your AFH, or sorry, the AFM, the airplane, the flying manual in the plane, to determine what kind of GPS you are. So WAAS, you don't need any other alternate means of equipment. So technically, if you have an in-op VOR receiver and that's your only other alternate means of navigation, with a WAAS GPS, you're good to go. Now again, that's assuming with a database current. Is RAIM necessary for an SPS GPS to be used IFR? So RAIM is necessary unless you have another alternate. So yes, you're going to need RAIM for an SPS GPS. So if you don't have RAIM, you're pretty much screwed. So again, if you don't have those 5 satellites, you have a big problem on your hand with one of these non-WAAS GPSs. Now a WAAS GPS, you don't need RAIM. Now chances are you're going to get RAIM anyways if you have WAAS available. But what happens is, because you have the WAAS GPS, you bypass that RAIM check. What types of approaches can you shoot? Well, with an SPS GPS or the non-WAAS GPS, you are limited to that LNAV. We're talking about GPS approaches, the LNAV, and obviously, circling LNAV approaches. Whereas if you have the WAAS GPS, you can now shoot LP or LPV approaches. And then finally, the alternate. So when flying an alternate in IFR, you're going to need another type of approach available. So if you're flying with a non-WAAS GPS, if you file that alternate, it better have something other than a GPS approach. So it must have something other than GPS. Whereas if you're flying a WAAS GPS, you can fly to an airport with only GPS approaches. For example, flying into Wadsworth, that would be a valid alternate. Let's maybe Wayne County. Wayne County would be a valid, Wayne County's a VOR. So Wayne County would be a valid alternate for this and this, whereas Wadsworth would only be a valid alternate for a WAAS capable GPS. So if you look into it, most Garmin 430s or 530s are going to be your GTN, you're going to be your C146C or your C129A. So that's what they are. Again, you can look on your own though. Okay, now some terms we need to know as well. So some terms we need to know. So rote terms we just need to know. So we need to know GNSS, GBAS, LAAS, GLOS, RMP, RNAV, PBN, and GLS. So I'm going to check while we're recording, but take a look at these. Okay, we're still recording. So GNSS is Global Navigation Satellite System. So GNSS, you just need to know all these acronyms. Okay, I know it's boring. GBAS, like we talked about, is your ground-based augmentation system. It's WAAS. Well, WAAS is Wide Area Augmentation System. LAAS, Local Area Augmentation System. Okay, these ones we should already kind of know by now. Now this one as well. So this was what? GBAS landing system. Okay, so now we have RMP, RNAV, and PBN. So what I'm going to do is I'm going to take these out. So first off, what is PBN? PBN stands for Performance-Based Navigation. Performance-based navigation. So it's just like it says, it's performance-based navigation. And so we can further divide these into two groups, something called RNAV and something called RMP. So RNAV stands for Area Navigation. And then RMP stands for Required Navigation Null Performance. Okay, so what's the difference? Well, RNAV, all that is really essentially going to and from different dedicated points. So for example, area navigation consists of something like this. So really, the whole point of these performance-based navigation is to limit ATC vectoring. Because imagine if we had all these planes, like all the thousands of flights daily, and all of them were just getting random vectors from ATC. That would be nonsense. That would be chaotic, right? And so how we can get around that is something called RNAV. So traditional RNAV will look something like this. So this was like your Victor Airways. This might be Victor 76, Victor 101, and these are two VORs. So from VOR to VOR is kind of your traditional RNAV system. We can then go into, instead of doing physical ground-based systems, we can do GPS RNAV. So again, RNAV doesn't mean GPS per se. Now it's associated with it, but GPS RNAV is going point to point between GPS fixes. So yeah, that's RNAV GPS. And then furthermore, we can have something called RMP. And what RMP is just a certain criteria that must be monitored and also acted upon. Okay, so it's like RNAV, but kind of on steroids a little bit. So for RMP to exist, you essentially need onboard measuring and onboard alerting capability. So you got to be able to measure something. You got to be able to measure what your navigational performance is, and you also have to be able to alert on it. Okay, so that's the biggest difference between these two. So it's essentially RMP, you can think of it as RNAV with, I guess what's the best way of putting this? Yeah, with onboard alerting and monitoring. So you can go look, and there's different types of RNAV. For example, RNAV1, RNAV2, RNAV10, which is like oceanic. So RNAV1 are typically for departures. RNAV2 is en route. And these go back to your sensitivity with your needle as well. So on your G5, with that needle where it says ENR, Well, that's an RNAV sensitivity of 2. So 2 nautical miles across center line. Okay, so where does RMP look a little different than RNAV? Well, if you notice, what I've drawn up here is RNAV leg right here, GPS RNAV leg, and also something called a RF leg, or a radius to fixed leg. So radius to fixed leg is like an arc, but using the GPS. Now these RMP, RF legs can only be flown if you meet these RMP criteria. So let's just get rid of this for a minute, and let's look at RMP a little more in depth. So RMP has, for example, those RF legs. So you need certain authorization to fly these RMP. Now you can have RMP 1, you can have RMP 0.3, and 0.1. These are examples of sensitivities, and this is nautical miles from center line 95% of the time. So that's how they measure it. So again, with RMP, we need to measure it. So your AMP, or your actual navigation performance, so let's just say our required today is 1 nautical mile, okay? So it's 1. And then the GPS is saying we have 0.05 nautical miles, AMP. So in this case, notice how our actual navigation performance is a lot tighter than what's required. So because of that, we're good. But let's say now we're flying an approach with 0.1. So our required, in RMP, the required navigation performance 0.1, but our AMP is now 0.2 nautical miles. In this case, what would happen is your GPS is going to pop up with one of those LOI flags or some sort of dead reckoning mode or whatever it may be, and saying, hey, I can no longer meet the required navigational performance for this leg. So what are the 1, 0.3, and 0.1? Well, 1 would be more like departures or stars, so that'd be SIDS or stars. 0.3 is sometimes you'll see this on the standard approach plate. So for example, it may say RNAV GPS approach. And then down here in the little table down here, it says RMP approach. And then you'll always see the LPV mins associated with that. So LPV requires a sensitivity of 0.3. So you need an RMP of 0.3. Now if you check your flight manual, in this case for Garmin's, they have a nice website. It's like support Garmin. If you just look up RMP Garmin support, they have a whole table of all their GPSs and then which RMPs you're allowed to shoot with that series. And then also the AC associated with it, FAA advisory circular. So in this case, if you have a WAAS GPS and it's a 430 or 355, one of those that are very common, you're going to be allowed to keep going down the RMP list all the way down to 0.3, which is going to be your LPV. Now, it can't do anything. Now, it probably could, but it's not certified because the system itself has to be certified for anything less than 0.3. So for example, this 0.1 refers to those RF legs, which are like this. So anytime you see a 0.1 sensitivity, what it's gonna look like on that approach plate is it's gonna be called the RNAV, let's just say 24 RMP approach. It's gonna say parenthesis AR. So instead of it being called a GPS approach, you're gonna see it's called the RMP AR approach for that runway. And so when you see that RMP AR, I'm instantly thinking, I can't do that if I have one of these GPS in. Why? Because I'm only certified to 0.3. So because it's an RMP AR, it's gonna have that 0.1 nautical mile sensitivity, which I'm not allowed to shoot. So essentially, you're good to go until I see RMP AR. And again, this refers to the lateral accuracy and nautical miles from the center line 95% of the time. So again, 0.3 and above, we can shoot. So that's RMP in a nutshell. And that pretty much is gonna wrap up most of the GPS discussion. Let me just make sure I don't have anything more. So again, RMP, you need to monitor it and you have some sort of alerting. So let's just say we are flying the RNM GPS with LPV mins. Well, what's that RMP tolerance? Well, the RMP tolerance is 0.3 nautical miles. If your AMP exceeds that, let's say 0.4 nautical miles, what will happen? Well, let's think about it. Well, you get the LOI flag on the GPS, so loss of integrity. So that's going to come up. If you have a 430, it could even go into dead reckoning mode. So like I said earlier, that's what you're going to expect to see if your AMP doesn't match the RMP. So that's the alerting system that Garmin gives you. Okay, so that pretty much wraps up GPS in a nutshell. Let me know if you have any further questions. Hopefully this makes sense. Thanks.